the aircraft is flying in the white regions. The information is obtained from a camera at the bottom of the aircraft, and as you see, as you go near to the ground, the collected information comes in front of increased resolution. On the other hand, the area covered is smaller, and information is obtained in various resolutions at a single image. If you obtain information from the same region by visiting the region more than once, you don't get additional contribution to the collected information, except the case where you get a high resolution information. The forbidden regions has been incorporated in the form of the penalty function into the cost function construction, and instead of choosing an on-off penalty, we have preferred smoothly rising penalty function value starting from the border towards the center of the forbidden region. The final point of the path is to be the starting point. So in the cost function, there is a final point requirement presented in the form of penalty as indicated. Dynamics of the unmanned vehicle, air vehicle, is taken into consideration implicitly. The basic variables of the optimization problem are the guidance directions, where the autopilot system expects from the guidance algorithm after the path is discretized at each second of the duration of the flight. But the resultant path is obtained after the dynamics of the aircraft is utilized. So, basically, if you look at the problem from an optimization point of view, we have a constraint optimization problem to deal with. And constraints are quite complicated. But there are important details. Most critical details are that the penalty weights are not constants. They depend on the region where the problem or path is going through, as well as the success of the problem. So the penalty weights are chosen as adaptively. Now, the main difficulty of the problem is that even though it is not apparent at the first glance, the optimization variables are implicitly depending on each other. Choosing the third variable affects the last variable or all the remaining variables. You can say it for all the other variables, and it is not easy to express this implicit dependency explicitly. So you can try the classical optimization algorithms, gradient-based, as well as the evolutionary algorithms, but I don't think you will have a feasible solution, even a feasible solution, after you run the algorithm for in a good computer for 10 days, for example. And actually we have tried, of course, dealing with the problem based on the classical well-known techniques, and the solution is couldn't be found by a standard approach. So, the basic difficulty is that the essence of our solution idea is based on finding the order along which the target is to be visited. Once the order, the optimum order, is available, the remaining part is relatively simple. Once the order is obtained, in which you have to visit your targets, I should say that we have imposed the condition that all the targets are to be visited. The next difficulty is constructing a path which maximizes the objective, minimizes the cost, as well as you have to satisfy the constraints such as visiting all the targets. You shouldn't visit or go over the forbidden regions. Final point is to be the starting point. Okay, let me first describe you the procedure of determining the visiting sequence of desired regions. The idea is utilizing the classical traveling salesman problem. The difficulty in using the traveling salesman problem is that you should construct you should give the distance matrix in order to deal with the traveling salesman problem. So we have approximately constructed the distance matrix by considering the distance between targets along piecewise linear paths which are supposed to satisfy the constraints. This is an approximate construction of the distance matrix. Then you see there are several alternatives. There are more than one way between two cities or targets, as indicated on the figure. Now you see on the figure the paths associated with the distance matrix construction, and on the right side you see the solution of the traveling salesman problem. The solution indicates the order where the targets is to be visited. Next, the traveling salesman problem is solved using a genetic algorithm, but it is actually just a simple method, one of the possible methods to deal with solving the traveling salesman problem. Anyway, after the seed path is obtained, where the visiting order of the targets is chosen, the seed path is obtained by just running the algorithm, model aircraft along the seed path. You see the initial seed path on the figure. Most of the requirements are satisfied, except the initial and final points are not the same. Some targets are not, may not be visited completely, and you see there are forbidden region violations. So the next stage of the optimization process starts here, where a genetic algorithm structure is preferred to optimize the actual problem after the direction and seed path has been found. Even though I am speaking about genetic algorithm is used, actually it is not very important in this analysis, because only the structure of the genetic algorithm is important. The job is performed by some intelligent or heuristic operators. Those operators are more than one. Actually, for the final three-dimensional multiple aircraft case, we have 7 or 8 such operators used for the minimization job. Idea is to incorporate the human reasoning into the path planning problem in the form of intelligent adaptive mutation operators. What are those operators? For example, one of them is pushing the path from a forbidden region. And it is simply described on the figure. One thing is important. If you push the path from a forbidden region by using such a mutation operator, you should also take care of the remaining parts of the path because they can be disturbed as well. Another operator is heuristic mutation operator is pulling the path into a target region, desired region, as shown. Structure is quite similar to the pushing operator, but it does the converse job. The final point consideration is taken into account in the form of a penalty, but the difficulty is that you should arrange the variables of the algorithm. Here is the result you see on the figure. I don't claim that it is the globally optimum path, but you can obtain the globally optimum path by running the algorithm maybe 1 or 2 hours more. That's another example. Again, it is a path, resultant path, quite close to the globally optimum path. I should say that these results are obtained in less than 5 or 10 minutes of computer time, which is very good when compared to a classical genetic algorithm running, which is unable to obtain the solution within 10 days for these problems. Also, I'd like to emphasize that the regions in our studies, as shown in this presentation, are quite complicated when compared to the regions used in path planning problems in the literature. I'm not restricted to using rectangular forbidden desired regions. Here is an example for a very, very complicated topology. One of the difficulties is that we'd like to be able to know the complexity of the path planning problem involved. And there is not a simple measure of complexity. We have been able to discuss the computational complexity of the problem based on the time duration it takes for finding the optimum or suboptimum solution. For example, the second region is region 2 is, even though they have the same number of targets in forbidden regions, second region is much more complicated when compared to the first region, and you can understand it by the time in the second step of the stage of the algorithm. The first problem region takes 4.6 seconds to obtain the solution when compared to 12.1 seconds to deal with the second region problem. Okay, what if there are more than one aircraft you should use or you can use in order to solve your path planning problem? And remember, the objective is to obtain as much information as possible. The trick is that we have to transform this very complicated problem into the problem we have already solved, that is path planning problem for a single aircraft. So the starting idea is utilizing the multiple traveling salesman problem. So using the multiple traveling salesman problem, a multi-aircraft path planning problem is transformed into path planning problems for multiple aircrafts, each of which is to be solved separately. So you see some very, very complicated examples for multiple aircrafts. This one is what the multiple traveling salesman problem suggests after the distance matrix is constructed. Here is the actual resultant paths after the dynamics of the aircrafts are taken into account. Next, these results have been extended to multiple aircrafts in the three-dimensional region. The idea is not very different, except our forbidden regions and desired regions are slightly more complicated because the height is to be involved. For example, a mountain can be a forbidden region. The aircraft may go either left and right part of the mountain, side of the mountain, as well as the aircraft may also go over the mountain. So the energy involved with the path is taken in addition to the account. So you can go over the top of a forbidden region by increasing your height, but this costs you additional energy, which decreases the length of the path. Collected information decreases, so you should prefer going either left or right side of the mountain. Actually, you can arrange it easily by playing with the penalty, adaptive penalty constants. Without giving the details much, I'd like to give you the results in regards to our three-dimensional multiple aircraft path planning problems. Here you're viewing the paths associated with each aircraft separately in three-dimensional representation. The forbidden regions are represented by black regions. Actually, I could have presented them as black columns, but then the path would be obstructed much, so you should visualize them as black columns. And the final, most difficult problem solution for our multiple aircrafts. Now, final extension of the path planning job is for the online path planning problem. And 2 years ago we thought that it was very easy to extend the offline results to the online one, but immediately we have seen that it is not so straightforward to extend the offline results to the online case, because you don't have the cost function. You have to solve the optimization problem, but you don't know what the cost function is. Because you should assign online the directions to the aircrafts to maximize the collected information, but you don't know the number of aircrafts, because some of them has already been assigned to certain paths or targets, and while you assign one aircraft to a certain target, suddenly one of the aircrafts visiting a target goes out of the target, finishes its job, and expects a target to be assigned to itself as well, and the previous assignment may suddenly become useless. because the new aircraft goes to the particular target in a very short time. Next, the dynamics of the aircraft takes too much time to perform the online path or target assignment. So we should first get rid of the difficulties presented by the dynamics, utilization of the nonlinear or linear dynamical models of aircrafts. The trick here is that using so-called Dubin's vehicles or Dubin's paths. Now, by using the Dubin's vehicle idea, a path is constructed using the kinematic information in a very short time, and the resultant path is expected to be very close to a path even when you use the dynamics of the aircrafts. That made the problem solvable in online. Okay. Next, the cost function construction is dealt with. We have to allow some free times for the aircrafts without a path planning assignment is done after they leave the targets. Okay. We have to take the future of the path planning problem in order to construct the cost function. This idea is similar to one of the classical control techniques known as model predictive control. And the forbidden regions can be avoided by one of our heuristic operators easily. And the assignment on real time is to be done using an approximate but very quick technique known as the Hungarian assignments, because basically we are dealing with the assignment problem. After the assignment is done, the aircraft finds its path very easily. In this example, you see 5 targets and 5 aircrafts, and if the rule we have utilized were not used, the aircrafts were supposed to going on circles without visiting the targets. After the basic rule is constructed and used, then the targets are visited in a systematic way by the aircrafts. This is the utilization of the algorithm on a very simple problem where the global optimum solution is known, and that shows us our algorithm works. Then I would like to show you some of our results. For example, here is an online path planning solution where one of the aircrafts is suddenly lost. Let me just show you this final solution where we have many targets and many aircrafts, and this is how the online path planning problem works as indicated by the paths on the figure. The previous 2 movies did not work here. There we had also presentations where the targets are moving as well. Usually you expect the resultant path for each aircraft to start becoming a periodic path, but it is not necessarily so for each aircraft. Anyway, uh, 2 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 What can be done for the path planning problem from this point on? The computational complexity problem still remains to be discussed. There are many things to be investigated for the online path planning problem, because we have just started to investigate it in this study. Additional operators can be defined in order to reflect the human thinking into the resultant optimization. And additional studies can be done where the targets are where targets are supposed to move. Of course, here we have presented all of our studies under the assumption that full information is available, and the problem is solved by a central unit, centralized unit. We may try to solve this problem in not necessarily central way. Each aircraft may contribute to the path planning problem from its point of view, decentralized way. Plus, the complete information assumption is not necessarily correct. Either we will be unable to collect information about the moving targets continuously, or the information to a central unit will not be presented completely while it starts solving the problem. So the research is expected to go in the incomplete information case. Some publications are made, and one of them is being prepared for the online path planning part. Okay, that's all. Thank you for. If you have questions, I can answer them, or I can answer them afterwards. Yes.
Now, as I understand, you have non-linear mobility, non-linear equations.
Yes.
Have you linearized these equations and solved them by repeat?
The dynamic model of the aircrafts were linearized. The only reason is that the computational time should be reduced in order to involve the dynamics. Problem is very, very highly nonlinear, and you cannot express this nonlinearity explicitly, so you cannot speak of linearizing the nonlinearities of the problem.
But how we lose some of the critical meaning of the original problem by linearizing it?
No, by linearizing the aircraft you don't lose the original meaning. The original meaning, actually, the nonlinearities involved from the path planning problem, not the dynamics of the aircrafts. The paths very, very will show you small changes, because even though we have linearized the aircrafts, the point of linearizing is not single. They are linearized, I think, at more than 120 points, and actually, the model is still nonlinear. Okay? Yes, of course.
I think this is a very interesting problem, and you have done a great job of doing very complicated optimization problems. I have two questions.
Yes.
One is related to these paths. All these paths depend on the air conditions, like aerodynamics of
Yes.
the vehicle and so forth. How are they included here? The second one is also, let me ask you the second question. This is a computationally very intensive problem, and genetic algorithms are very easy to parallelize. Are you using parallel algorithms here to get faster solutions? Those are my questions.
Yeah, coming to the, starting from the first question, actually we discussed taking the weather conditions into account. For the offline path planning problem, we assume or estimate the weather conditions. That is how they can be taken into account, and the resultant path will automatically reflect the air conditions, especially paths will slightly change under the effect of wind. The air conditions, especially the effect of winds, is very important, especially in the case of the online path planning problem, but they can easily be taken to deal with, because you know where your aircrafts are at each instant of time, and you perform the assignments online. So you will, whether their paths are not exactly according to what they want to visit, since you are continuously doing the path planning job, this is how we expect the air conditions can be dealt with. Or we may also include the disturbed perturbation in the paths because of the weather conditions, as long as the direction of the winds are known or estimated. The genetic algorithm can be parallelized, okay, because its structure is open to parallelization, but I don't think you will be able to find the answer easily, even for the offline problem, in a short time, even if you parallelize, because the difficulty is not the computational time. Okay? Difficulty is that the implicit dependency of the optimization variables to each other. You are not giving information to the genetic algorithm about this dependency. It is implicit in a problem construction of path involved with a chromosome. So parallelization will not be a solution. Actually, we have done a simple job of parallelization and it didn't work. Any other questions?
Thank you very much for your very interesting speech. I want to ask one question related with your optimization algorithm. Which language program did you use in optimization?
Actually, we have made all the programming in MATLAB and Simulink.
Thank you very much.
Thank you. If I understand correctly, there is a map of some regions, desired regions and forbidden regions. If this understanding is correct, how the UAVs know the coordinates of these regions during practical application?
That is the navigation job. We didn't consider the navigation job explicitly. It is in fact not directly related to the basic issue of the research problem we have discussed. It is an important part of the online path planning problem, but again, it is out of the context. But if you are dealing with this problem in a realistic framework, you should consider the navigation as well. Okay. I think that's all. For the last question.
As I understand, all the algorithm works in real time, yeah, in run time. However, the computational time, as I see, is 4.6 seconds on a 4 point. It's, I think, not good to work in real time, you know.
The
How about
computational times I have made for the offline problem were valid for the offline case. And for the offline problem, those times are very small. The online path planning problem is solved in less than 1 second at each second. Actually, we don't have to solve the assignment problem in less than 1 second. Actually, it is to be solved in 5-second intervals. That is the duration which is quite feasible. And we solve the assignment in less than 1 second for the online problem. So there is no problem with the computational time. Okay. Thank you for listening.
I would like to thank our invited speaker, Professor Dr. Levricioğlu, for his speech. Now we will have our coffee break right outside the conference hall, so please join us. Thank you.